All right, hey, organic chemistry. So I wanted to help you with your exit ticket and generating different structures or isomers of hydrocarbons. This could require a little bit of thought and trying to manipulate these hydrocarbons. So the question says generate 5 different structures for a hydrocarbon that contains 6 carbons and 14 hydrogens. I'm going to let you know that if it has 6 carbons and 14 hydrogens, it definitely follows the CnH2n plus 2 rule, which means that it's an alkane. So all single bonds. I'm not going to have a double bond. I'm not going to have a triple bond. I'm not going to have a ring. I'm going to have all single bonds. Okay? So if N was 6, H would be 14. We're good to go. So let's start by drawing the first easiest structure, which is a straight chain of 6 carbons. 3, 4, 5, 6. Okay? And everything else is going to be a hydrogen. This is just like in the video you watched before you got here, where you draw the whole blown out structure, and we're going to name it. This will be our first structure. And another way that you can draw these compounds is the same way that we've been drawing them. 1, 2, 3, 4, 5, 6. 6 carbons in a straight chain, all single bonds. This is definitely hexane. This will be one of 5 structures that you could draw. Okay? Now, just like in the video, and this is the manipulation, and it doesn't matter what order you do, but one way to try to make an isomer or a different structure with the same molecular formula is if you take the N carbon that technically looks like a methyl group and switch it with a hydrogen on the inside. So I'm going to switch this carbon on the end with this inside hydrogen. Now, if I switch it with this hydrogen, I get the same compound, right? If I put this carbon here, basically I'm going to have 6 carbons all in a row, just like I just had before. It just looks like it's bent. Okay, so now if I draw that, 2, 3, 4, 5, 6, okay? Oh, not 6. 1, 2, 3, 4, 5, and then a hydrogen goes here, right? Because I switched the hydrogen on the end here. And then I put that CH3 here. There we go. 1, 2, 3, 4, 5. I'm going to have 6 carbons, but right now my longest chain is 5, and you'll see that. Okay. And now I'm putting in all of the hydrogens. Oops. All right, so all I did was I swapped this hydrogen and this carbon. And now it looks like this carbon is on my 4th carbon in. If I wanted to draw this in bond line drawing, I would have 5 is my longest chain, and you'll see that. And on my 2nd carbon in, it'll be there. Now, I'll tell you where I get 2nd from, okay? Now, I could count longest chain is going to be 5. Doesn't matter. I could go 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. I'm going to get the same thing. So my longest chain is 5. On my 4th carbon, I have a methyl group. But we should remember that I should number it right to left and left to right. So I could do 1, 2, 3, 4, 5. And this can also be 2-methyl. Which do I choose, 4-methyl or 2-methyl? You should remember that we choose the lowest number for our substituent. So this is going to be 2-methyl. 5-carbon chain, all single bonds. That gets pentane. My parent name is pentane, and this is 2-methyl. So 2-methyl pentane. 1, 2, 3, 4, 5. Methyl group. Okay? That is a second structure. I want you to try and draw 3 more structures now doing the same thing. You should get or be able to get 3 more. Now you could move another inside methyl group. You could move this methyl group to the middle. I would say you cannot move it here or here because it'll be the same as it being here or here. So you could probably move it in one more time. After you move it in one more time, I would keep it there and move another methyl group onto the inside and then try and name those structures. Okay? Then let's look at part 2. In part 2, it says generate 2 structures. I'm just going to do 2 that contain 6 carbons and 12 hydrogens. This follows the CnH2n rule. So if N was 6, H would be 12. These are alkenes, I mean. So there could be a double bond. And you can put that double bond anywhere. So I'm gonna draw the structure simply like this. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And just in case, I'm gonna put in the hydrogens. One hydrogen here, 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 and finally there are 3 on the end here. If I go and count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. C6H12. And this name, since I put the double bond C on the first carbon, this is going to be 1 pentene. Sorry, 1 hexene. Darn it. 1 hexene. If you can't see that, 1 hexene. 1 because the double bond starts on the first carbon, and that's going to be my lowest number for this. I want you to try and draw one more structure that has 6 carbons and 12 hydrogens. Now you could move the double bond, or if you want, you could just move like a methyl group somewhere else. You're still going to get C6H12 if you have 1 double bond and then all of these carbons and hydrogens. And then the last one to think about, and this is what we're going to think about for tomorrow. If we have twice as many hydrogens as we do carbons, must we always have an alkene? Let's look at this structure. There are 1, 2, 3, 4, 5, 6 carbons. Don't forget that each corner and edge is a carbon. And then every carbon needs to have 4 bonds. If there aren't bonds shown, then they're going to be hydrogens. So right now this carbon has 2 bonds. That means it's got 2 hydrogens. All of these actually end up having 2 hydrogens. Okay, so this actually has the molecular formula C6H12. So it says how many carbons and hydrogens does this compound have? 6 carbons, 12 hydrogens. Is it an alkene? Is there a double bond? This is asking, is there a double bond? And the answer is no. What is different about it? It's a ring. What is its name? Well, if you remember how to name a 6-carbon ring, all single bonds, this is cyclohexane. Now, this is an isomer of 1 hexene. So it is an isomer of 1 hexene. Why? They both have the same molecular formula, but you could clearly see that they both are definitely arranged differently. Another answer that you would put here will be another isomer of cyclohexane. An isomer, what we call a constitutional isomer, is different connectivity, same molecular formula. All right, so this was just a bit of help with your exit ticket. If you need further help in trying to figure out more of the structures, you could just call me over or let me know.